Happy Friday, everyone. I hope you have gotten or will get a chance to enjoy the unexpectedly beautiful sunshine today. Have some birds for you. Birds are cool. These birds are black skimmers on the Georgia coast. And the sharp-eyed among you may have noticed they have an unusual beak. The lower bill is much longer than the upper bill. This is because they get food by skimming along the water and kind of trawling for fish that are too slow to get out of the way. And they come up with a meal. So that's the black skimmer. Wanted to mention that I have added a couple links to the Moodle to get directly to the lecture recordings, to the playlist where I'm putting them on YouTube, and then also as soon as I finish recording them here, they go up to Panopto. So if you are reviewing it immediately, you'll see the raw, uncut, straight from the source, Panopto. I then do some editing, and that's what ends up on YouTube. So you can find those there. Any questions on the lab, the quiz, any of the integer stuff that we've been looking at? All right. So there are a couple kind of major topics for today. The first that I want to talk about is how floating point numbers are represented in a computer's memory. And back when computers were first being developed, a computer was a highly kind of specialized, purpose-built machine, and different companies were sort of coming up with their own way to represent floating point numbers. Why would this not be good in the long term? Why wouldn't we want different companies sort of having their own way of doing it? Why?
Well, I mean, because then they're incompatible across, machines.
Yeah, where I run a program on my laptop, it gives me a different number than when I run it on a lab computer. And yet a different number when I run it somewhere else, so we need some sort of standard. And the kind of standard that has been adopted everywhere, and that has sort of specialized circuits that are part of CPUs to handle this one is the IEEE 754 floating point representation. IEEE is an international engineering association, so engineers around the world got together, came up with this standard, and there are kind of two competing concerns here. We have accuracy versus efficiency. And if I'm a scientist and I want to run some program to compute scientific results, analyze scientific data, I might care a lot about accuracy. I'd be willing for the software to run more slowly if it gives me really precise results. Whereas if I'm an engineer, I might care that the software is efficient, uses less memory, runs faster, and I'd be willing to accept some amount, not an unbounded amount, but some amount of error in order to get this efficiency. And given a fixed width, given a fixed number of bits to represent a floating point number, could we achieve perfect accuracy? No, there's inevitably going to be some values that we can only approximate given a fixed number of bits. But given a fixed number of bits, this IEEE standard kind of leans more toward accuracy than it does efficiency. An important takeaway from this is that a program that does a lot of floating point arithmetic is going to be slower, typically, than a program that does a lot of integer arithmetic. Like floating point, just because of the mechanics involved, like 2's complement, we can have circuits that kind of just take all the bits and do the various arithmetic operations. Like we have dedicated circuits for floating point, but they are necessarily more complex and thus tend to be slower. What do you think?
Is a floating point, is it just anything with a decimal?
So that's a good question. So what we're really concerned with is like we'd like to be able to represent real numbers on computer systems. And this is just sort of the mathematical category of numbers that we want to be able to, for example, to represent all values between 0 and 1. Compared to with integers, we can just do 0 and just do 1 and nothing in between. So real numbers are kind of the full range of numbers, not complex or imaginary numbers, but real numbers. So this term floating point, as we'll see, comes from the fact that we're not going to, so let's get into kind of how this representation is going to work, and we'll see kind of where this term floating point comes from. So I want to start with a more general idea. And that is representing numbers in scientific notation. Can someone explain what it means to you to like write down a number in scientific notation? Okay.
We express some number as like c times 10 to the n.
Yeah, we have some value, and we're representing it as times 10 to some power. So if I have 10,762.53, putting that in scientific notation, I typically move the decimal to give kind of just one place, just one digit to the left of the decimal. I get 1.076253 times 10, and kind of how would I know what the exponent for 10 would be in this case? See?
How many digits you move over the decimal?
Exactly. Each factor of 10 kind of moves the decimal point to the right if it's a kind of factor above 1, or to the left if it's a factor below 1. And so I had to kind of turn this back into the value. That would be 4 places. So 1 point such and such times 10 to the 4th. Does this make sense? Questions on this? So I'm bringing this up because when we look to this IEEE 754 standard, we are going to use kind of the binary form of scientific notation. Now, can anyone think of a reason why, given a fixed number of bits, we might prefer to represent something in scientific notation rather than just kind of the full, like the using bits to represent kind of the full non-scientific notation value? So,
It's really good at representing enormous numbers and tiny numbers.
Exactly. That if I have, say, the number 1 trillion in base 10, if I wanted to represent kind of 1 trillion with kind of just as written here, I could not represent that in kind of our 2's complement 32-bit integer. Kind of goes kind of past the largest number we can represent. But if I say 1 times 10 to the 12th, now in some sense I need to represent the number 1 and the number 12, and this times 10 can be sort of implied by the representation. And so I can take, as Lev said, an enormous number and turn it into something that deals with much smaller quantities. And similarly, if I had 1 trillion, 0.00000000001, I could say 1 times 10 to the negative 12 would represent a number much, much smaller than that. And since part of the goal of floating point is to be able to represent not only real numbers, but a huge range of numbers, both very small and very large, scientific notation is very useful for that. All right. So how does this actually work? Well, one part of it is since we're dealing in binary, we're going to use the notion of a binary fraction. And we're used to saying kind of this point right here is the decimal point, because this is a decimal number, a base 10 number. So in a binary fraction, we have the binary point, which would separate, say, we have 0b to indicate that it's a binary number, and then maybe 0.1011. And here, just like our ones to the left of the decimal point, our powers of 2, our places to the right of the decimal point are powers of 2, just this time negative powers, because they're increasingly smaller fractions. So we have 2 to the negative 1, or 1/2 place, 2 to the negative 2, or 1/4 place, 2 to the negative 3, 2 to the negative 4, and so on. So this number would be 1/2 plus an 1/8 plus a 16th. So I think would be 11/16. And so how this works in our IEEE representation is that for a single precision number, which in C is written with the type float. Anyone remember how many bits are in a float? Rebecca?
Is it 4?
4 bytes is absolutely right. How do we turn that into bits?
32.
So we have a float that's 32 bits. We're going to divide those bits up into the following pieces. The first bit, and I told you that our floating point would use sign and magnitude, is a 1 if the number is negative, a 0 if it's positive. So this is our sign bit. Our next 8 bits are the exponents. So this is where our scientific notation comes in. Our remaining 23 bits are the fraction. And the idea is that we have -1 to the power of this bit s. So if s is 1, we'll have a negative number. If s is 0, this will be 0, times 2 to some exponent. Maybe I'll instead write it as times m times 2 to some exponent. And this m here stands for mantissa, which is a kind of fancy term for the this portion of a scientific notation number. So these exponent bits are used to generate E, these fraction bits are used to generate M, and the sign bit is used to generate the sign. Yeah.
So for the fractional component, like in normal scientific notation, you're sort of taught to do like, 1 point blah 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 or like 2 point blah blah blah. Are we just doing this as like point some fractional component, just raising the exponent by 1 to account for that?
Yeah. So I think there are perhaps diminishing returns on getting into like the really fine-grained details of how this works, because there's all sorts of special cases and it's a bit messy. But the textbook has all of this if you're interested. But yeah, so this fraction is just the digits after the binary point, and we add 1 to that unless all the exponent bits are 0, in which case we don't add 1 to it. And there's a figure. There is these sort of two different modes have names. Normalized exponent is non-zero. We add 1 to the fraction bits. Denormalized exponent is 0. We don't add 1. This is a way of kind of representing very small numbers in a kind of predictable and uniform way. And then normalized is what allows us a huge range and to get very, very large. Kevin.
Wait, so the 8-bit exponent represents the mantissa, and then the fraction represents the E?
The 8-bit exponent are used to generate the exponent, E. And then the fraction bits are the mantissa or 1 plus the mantissa, depending on whether they're normalized or denormalized. Again, the details of all these different kind of modes are less important than this general idea that we're kind of separately representing an exponent and a fraction. That lets us both get to very small with negative exponents and very large numbers. What other questions do you have? So there are two special, besides normalized and denormalized, there are two special values that this can represent. If the exponent is all 1s, if the exponent is all 1s and the fraction is all 0s, then we have positive and negative infinity. So, for example, if you, in this floating point representation, you divide a float by 0, it will actually give you infinity. It also has if the exponent is all ones, and the fraction does not equal 0, that's our other special value, nan, which is short for not a number. And this is to kind of represent quantities that just like don't exist in this IEEE format, which might include the square root of a negative number, isn't a real number, can't be represented, and so it would show up as not a number, potentially. All right. Questions on any of this? Fine.
So, the stuff you've written down below is for denormalized?
This stuff here, normalized and denormalized, these are two other modes
I see.
that are separate from these two.
I see.
Yeah, so note that these both happen when the exponent is all ones. Denormalized is when the exponent is all zeros.
Okay.
And so if the exponent is anything besides all zeros or all ones, then we're in normalized.
Okay.
Other questions? All right. Last thing that I want to say about floating point is there's this floating point sort of converter / simulator, which is linked from the notes on the course webpage, and it allows us to see how does this single precision represent different numbers. So I can say, okay, give me 0. And I see, well, all the bits are 0, as you might expect. I can say, give me 2, 3, 4, 5, 6, 7, 8. And I can see the exponent is giving me 2 to the 21st. The mantissa is giving me this fraction here, and it turns out that I can represent this number exactly. There's kind of no error in taking the real number 2,345,000 into a floating point. But as I get bigger, I start not being able to represent the number accurately. And you can see that actually the closest I can get to this number somewhere above 2 billion is I can get within 52. Can't do any better than that with these 32 bits. And as I go farther and farther away from 0, either in the positive or negative direction, the error gets bigger and bigger. So I add another couple zeros, I can get within about 3,000 of the actual number. And this is kind of true of very small numbers. And see that I can't represent kind of 1 times 10 to the negative 8 exactly. I can get close. An error kind of way in the kind of 17th decimal place. There are, of course, some numbers that I can represent exactly, like 1 over a power of 2, like 1/8. That I can represent exactly here. And when I'm doing arithmetic with these floating point numbers, it will typically round to an even number if it can't do it exactly. Rounding to even, as I think in terms of kind of the last digit of precision, kind of helps avoid bias that you get by always rounding up or always rounding down. If the value is too close to 0 for the representation to handle, it will just give you 0. If it's bigger than it can handle, it will just give you infinity. Typically, unless we're very concerned about memory, we would want to use the double type, which is the 64-bit representation, because that's going to give us a much bigger range of numbers, significantly less error, and so that adds 3 more bits to the exponent and almost 30 more bits to the fraction. All right, that's all I have to yeah, Marcus.
How come like the error is always like either positive or negative and not like both? How come it's like plus 52, or sorry, negative 52 instead of like plus or minus 52?
Because it's not necessarily symmetrical. Like the closest value, if I go back to 2, 3, 4, 5, 6, 7, 8, 9, 0, 0, negative 52. So the closest it could get was a value that was 52 below. The kind of next number above that it can represent appears to be like 56 above. And so it's kind of not necessarily that it's the same distance away in either direction. And because it will kind of round to even in terms of the binary, so kind of round to have the last digit of the fraction be 0, it will just kind of choose the kind of corresponding value that way. So yeah, kind of based on the rules of the representation, it will always like be off in a certain direction given a number you're trying to represent. Does that make sense? Angela.
Can you explain what single precision means again?
So this is kind of historical terminology. Like there at one point was just the 32-bit version, and then once they added the 64-bit version, then you had to kind of name like give these two different things a name, and so the IEEE standard defines a single precision representation, which is 32 bits, and a double precision. Yeah, that's what I forgot to change. Once we move to double, that's our double precision representation with 64 bits. Other questions? All right. So before I get to a new set of operators that we're going to use to manipulate bits and booleans in C, I want to tell you about the first time the son of the U.S. president was himself elected president. This happened in 1924. John Quincy Adams, the son of John Adams, the second president, was elected president. And you may be looking at this electoral college map, and you may say, well, it really doesn't look like Adams won this election. And that would be an astute observation. Adams got both fewer electoral votes and fewer actual votes than Andrew Jackson, one of his competitors. So just to put some faces to names, here's John Quincy. Here's Andrew Jackson, who you might know would become president later. And here's another sort of important figure in American history, Henry Clay, who also made his first of 3 unsuccessful attempts at becoming president in 1824. And so, why didn't Jackson win the election? Well, he didn't have a majority of the electoral votes, so the House of Representatives got to decide who won. Henry Clay was very influential in the House of Representatives and supported Adams. Adams Adams then made Henry Clay Secretary of State, so there were a lot of accusations of corruption about this arrangement. Should also say that John Quincy Adams was one of several presidents in a row who were all Secretary of State and then President. So there was kind of a good run for Secretaries of State. The last person to make this switch was James Buchanan in the 1850s. So it's been a hard run for Secretaries of State since then. Adams and Jackson had a rematch in 1828, at which point Jackson absolutely crushed him. This was also an election in which the number the people who could vote were dramatically expanded. It was still only white men, but property requirements were basically dropped. So many more people could vote than in previous elections. Something else that you may have picked up on these maps is, why does Virginia have this weird shape? Don't worry, we will get there. And just because it's fun, I thought I'd throw in a couple decades later when photographs became feasible. This is John Quincy Adams, Andrew Jackson, who was one of our presidents with kind of the most medical issues. He had a lot of war injuries. He was not a super healthy guy when he was president. And then here's Henry Clay, looking a lot different several decades later. Passage of time. All right, that's our U.S. history for today. All right, get out of here. There we go. All right, so two kinds of operations that I want to talk about today that are new. The first is bitwise operations, which are so called because they operate on kind of individual bits or individual pairs of bits. So let me say a bit about why we care about these operators. In a computer system, all of the sort of circuits and things that we're using to do this computation are made up of transistors. Transistors are individual pieces of a circuit that can either have a high voltage or a low voltage that is running across the transistor. And this high voltage is nicely corresponding to a 1, and a low voltage corresponding to a 0. And because this is the way that we assemble the components of a computer system, it can be very efficient to have operations that work on this kind of level of individual bits. And as we'll see when we start looking at assembly, when the C compiler is turning your program into something that the computer can actually run, it will prefer to use bitwise operations wherever it can, because they tend to be faster and use less power than kind of something like multiplication or division. So what are these bitwise operations? We have bitwise AND, which is the single ampersand. Or, just to denote a single pipe. This is the character kind of above the enter key or return key on those keyboards. We have NOT, which I mentioned last time. Anyone remember what the symbol for NOT is? See some people making the signs. Why?
Is it the, no, wait, no, I don't remember. I lost track of it.
Kevin?
Just the one to the left, the number 1. Tilde, I think?
Exactly, yes. That's a tilde, and we also have XOR, which is, I think it's the circumflex or above the number 6 on a keyboard, the little hat.
Caret.
Caret, yes. All right. So what do these operations mean? And for and, if both of the input bits are 1, the output bit is 1, otherwise the output is 0. Or, as you might expect, is if either of the two input bits are 1, the output is 1. But if both the inputs are 0, the output of OR is 0. Not is a unary operator, which means it just applies to a single bit. It doesn't have two inputs, just one input. And it just inverts the input, meaning a 1 goes to a 0, and a 0 goes to a 1. And finally, XOR. Which stands for exclusive OR. Says if the inputs differ, meaning if one of the inputs is a 1 and the other is a 0, then the output of XOR is 1. Otherwise, if both are 1 or both are 0, the output is 0. These definitions make sense. I'll go through some examples, but any questions at this point? What?
Is there sort of an exclusive, or sort of an inverse and? So like if they're both false?
So I think if we combine not and we get this sort of NAND, or kind of inverted and. We can also combine not with or, which is actually has a different behavior than exclusive or. If you ever look into digital logic, how to assemble circuits, not and not or are kind of really fundamental building blocks for this. Other questions? All right, so so these bitwise operations, for our 3 binary operators, operate on inputs of the same width. So in my examples, I'm going to be dealing with 2 inputs, each of which is 8 bits long. In C, if you apply these operations between inputs of different width, it's going to first convert the smaller one into the same width as the larger one before it does the operation. So for our bitwise and, let's say we had 1, 0, 1, 0, 0, 1. And we can just look at sort of each pair of bits. None of the pairs of bits affect any of the others. So 1 and 1 is 1. Everything where they're not both 1 is 0. I'm kind of looking at each pair of bits to do the bitwise and. Does that make sense? Or works very similarly. I'll just do another example, this time with XOR. So for this first pair, what would the output of XOR be? Yeah, because it's only 1 if we have different inputs. So 1 XOR 1 is 0. How about 0 XOR 0? 0, 1. Exactly. If I have some quantity A, I take it XOR A, what do I get out of that?
0.
Yeah, it's going to be all zeros, because all the bits will match, none of them will be different. What if I do A XOR not A?
1.
Yeah, that will be all ones. So if we're dealing with 2's complement, A XOR not A will actually go as -1, no matter what A is, because it's going to give us all ones. And I mentioned last time that we could use not to compute an additive inverse. Because if I do A plus not A, that is going to be all ones. A plus not A, all the spots where A was 0 become 1, so I'm going to get 1 in every bit. And all ones is -1. And if I do some algebra, add 1 to both sides, A plus not A plus 1, that's going to give me 0. That's 1 plus -1 is 0. And then I just subtract A from both sides, and I get not A plus 1 is -A. So we can use this bitwise operator, which, as I mentioned, has some advantages in terms of efficiency to get an additive inverse. All right, let's talk about a couple more bitwise operators. And these are kind of a new category of operators called bit shifting. And we have left shift, which is represented by kind of 2 less thans. And this is going to take the bits of our quantity and shift them some number of spots to the left. So if I have A is this same 8-bit quantity, and then I say A left shift 2, I'm going to take these 8 bits and sort of shift them 2 spots over. So I've kind of shifted my 8 bits 2 spots over. I have 2 sort of new places and 2 that have gone past the end. Any guesses what happens to these ones that are shifted past the end?
Just go back to the, well, like, after
They-
finding the empty spots.
That is a very interesting idea that they might go back around. That is not the behavior of left shift, but that would be a sort of an interesting kind of circular shift operation. Heard someone else say they get discarded, which is sort of how fixed width representations will usually work, is stuff that goes off kind of either side just gets thrown away. And then we fill in with zeros in the new spot. So we also have a corresponding right shift operator. Works very much the same way. A right shifted by 2, have 2 new places. We have 2 that are kind of shifted off the right side, which we're going to throw away. And then we have 2 places to fill. And we actually, our left shift, we always fill with zeros. Our right shift, that's not necessarily true. We have 2 ways to fill these in. We have what's called logical right shift. And that fills with zeros. And this is what is used if the quantity we're shifting is unsigned. We also have arithmetic right shift, which is going to fill with copies of the sign bit. And as you might expect, this is what is used when we are shifting a signed quantity. So if we were doing a logical, if a was, say, an unsigned integer, we'd use our logical right shift, we'd fill with zeros. If a was, say, an int, a sign, well, it's 8 bits. So if a was a char, a signed 8-bit integer, what would we fill these places with?
A 1 and a 0.
So which one would be 1, which one would be 0?
The first one, the most significant.
This would be 1, and this would be 0, you're saying? Why do you say that?
Because I'm thinking the first number was a negative number, so to make it assigned, we just put the 1 for it to be a negative number, and then the 0. I'm just thinking fill it in with the 0.
Yeah, so that's on the right track. That if we interpret this as signed, you're right, that it is going to be negative, and then when we right shift, we're going to keep it negative. And you can think of these shifts as sort of going one place at a time, and we're going to follow these rules each time. So in that case, we shift it one time, we fill in with a 1, and then we shift it kind of the second time and also fill in with a 1. So for our arithmetic shift, you will set they'll always be filled with sort of all the same, either all 1s or all 0s, based on whether it's kind of a positive or a negative number. Does that make sense? So can anyone think of what does it do? Let's say I have a equals 5, and then I do a left shift 1. What does that do to the value of a? Like, what's an equivalent mathematical operation? Anders?
Does it double it?
Exactly. Kind of shifting to the left. You can think of it just like we're shifting a base 10 number to the left. We'd multiply by 10 kind of every time we kind of add another 0 as we fill in. Since we're in base 2, every time we shift to left, we're multiplying by 2. And if we look at the bits, this is 5. We shift it to the left once, and we're left with 8 plus 2 is 10.
And that's only when you don't discard any ones, right?
Exactly. So we double it modulo the kind of maximum value. So in this instance where I was shifting off ones, it's going to double it but modulo the maximum, so we'll actually wrap back around. But I bring this up because I mentioned bitwise operations, more efficient, and so if a compiler can replace the multiplication you wrote in your C code with a shift, it will do so, because shifting, kind of, when we're talking about the circuits involved, considerably simpler than kind of general multiplication. If left shift multiplies by 2, what would right shift do? Yeah.
Divide.
Exactly. So right shift's going to divide by 2. Of course, we're dealing with integers in this example, so divide by 2 rounded down. But useful to keep in mind that shifting can do this kind of multiplying or dividing by factors of 2. Any other questions on this? Yeah.
I guess for the right shift, I'm confused. If you put into the blank slots all ones, and like how can we tell if it's like a negative 11111010, or like how can we maintain the same number if that's the case? Like how do we read it?
So we wouldn't maintain specifically the same value because it's going to in effect divide by 2, but it will maintain the sign. So if it's a negative number, meaning it has a 1 in the most significant bit, it will stay negative because there will still be a 1 in the most significant bit.
Okay, got it. Thank you.
Other questions? All right. So I brought up, when I first started talking about bitwise operations, the terms and or. This notion of and or might be different. Is there a notion of and or that we kind of expect to be in a programming language that's different from these? Yeah. What is that? What is the and or that I haven't talked about?
Is it Boolean logic?
Exactly, and or that deals with kind of true and false rather than kind of bit by bit. So we do have Boolean operators in C. We have Boolean and, which is written with double ampersands. We have Boolean or, written with 2 pipes. And we have Boolean not, written with exclamation point. Does anyone remember what I said earlier about how true and false are represented in C? Rebecca?
I think you said that false was represented as 0, and then any other value is true.
Exactly. And we can really see this if we consider not hex 41. Because hex 41 is true, and not true gives us false, which is 0. And if we have hex 55, Boolean and hex 0, that's just going to give us 0. Because true and false is false. How about hex 55 or hex 0? Any predictions on what this will result in? Holly?
X55.
Hex 55, that seems like a reasonable outcome. Any other predictions? Trevor?
X1.
Hex 1. So I think hex 55 would be the more reasonable output, but alas, it's going to be hex 1. Basically, any Boolean operation in C, either going to produce 0 or 1. Regardless of what the inputs are, the output will be either 0 or 1. Does that make sense? Questions on it? What do you think?
If it only outputs 0, 1, why does it matter that anything else besides 0 is true, as opposed to just being like 1 is true?
Because the input to a Boolean operation can be something other than 0 or 1. It's just the output is always 0 or 1. So we need to, like, if we want to be able to have inputs that are not, like, we could restrict it and say the only things you're allowed to input into these Boolean operations are 0 or 1. But instead we're saying you can input any value. We're just going to interpret anything that's not 0 as true.
Just hex 0 is the same as null, right?
Yes. So if we're talking about capital null, that gets replaced with 0 passed to a pointer. So it's different from 0 in that it is considered a pointer type, and so the compiler will warn you if you're doing something with null in combination with something that's not a pointer. What's that?
Sorry. What about the like, I think you call them macros, the true and false like words that you can just type out. What do those like actually represent, I guess?
So later versions of C actually added a bool type, and you can write true and false. I've actually not looked into what that actually compiles to. My guess is that's just going to compile to 0 or 1. But the other possibility is that in some cases it would actually use just a single bit where it could, rather than some larger number of bits that was corresponding to kind of one of the integer types. Other questions? Go.
Is there any difference between like hex 0 with 1, 0, or 2? Like as you wrote it up there.
Yeah, so I'm not intending any difference in this example by it. What I had in mind for these examples was each of these were 8 bits, which would be 2 hex digits. But often, kind of leading zeros get omitted or get left out. And so, just like hex 0 might in fact stand in for like 64 bits, all of which are zeros. It just left out all the other zeros. Any other questions? All right, that's all I have for you today. Next time we'll look at a few more. We'll do some practice with these operators, and then we'll begin our journey into assembly. Finish up Lab 0 over the weekend, do Monday 9 p.m. I'll see you then.
Thank you.